Picture this, a hidden vault, right beneath our feet, capable of holding 150 gigatons of a seemingly invisible threat. 150 gigatons. That is a staggering number, and it isn't just a random statistic. It actually represents the estimated carbon storage potential hidden deep beneath the surface of India. It's a massive figure, and it might just be the key to solving one of the most pressing challenges of our time. To understand why that 150 gigaton capacity is absolutely crucial, we really have to look at the immense global stakes right now. As the study points out, developing nations are projected to account for 59% of global energy growth and 94% of coal consumption increase by 2030. India requires coal and fossil fuels for critical, near-term economic and energy growth. But at the same exact time, they've committed to reaching a net zero carbon footprint by 2070. So reconciling those two realities creates an incredibly urgent need for massive, effective carbon capture solutions. Welcome to This Explainer. Today, we're exploring a genuinely fascinating recent paper by Jyotirmoy Malik and colleagues, published in Geoenergy Science and Engineering. We're going to look at what sounds like a literal magic trick, the science of taking greenhouse gases and permanently transforming them into solid rock, right in the heart of India's Deccan Trap. Okay, let's dive into this. Here is our roadmap for today. First, India's massive carbon challenge. Second, turning gas into solid stone. Third, inside the Deccan Traps. Fourth, sponges, pipes, and rock. And finally, a pathway to net zero. Section 1. India's massive carbon challenge. As India's economic growth accelerates, bridging the gap between current energy needs and future environmental security is incredibly difficult. And a big part of that comes down to how we actually store carbon. See, traditional carbon capture and storage, or CCS, often relies on things like saline aquifers or depleted oil wells. Basically, it pumps CO2 underground and traps it under a physical seal, like a tight layer of rock. It works, sure, but CO2 is buoyant. It always wants to rise. If that physical seal cracks, the gas escapes right back into the atmosphere. But basalt CCS behaves entirely differently. In continental flood basalts, we aren't just trapping a bubble of gas under a lid. The CO2 actually chemically reacts with the rock and becomes a permanent solid mineral, no risk of it floating away. Section 2. Turning gas into solid stone. Which brings us to the core mechanism behind this incredible proposed climate solution. The technical term here is mineral carbonation. It's the process of permanently immobilizing CO2 as stable carbonate minerals through chemical reactions with silicate rocks. Because basalt is highly enriched in calcium, magnesium, and iron, it basically acts like a giant chemical catalyst. When CO2, mixed with water, interacts with these rocks, the basalt dissolves slightly, releasing those metals. They then bond with the carbon to form solid carbonate minerals, like magnesite or siderite. Previous projects, like Carbfix in Iceland, actually showed that this specific type of rock could convert over 95% of injected CO2 into stable stone in under 2 years. It's safe, it's fast on a geological timescale, and it is permanent. Section 3. Inside the Deccan Traps. And this brilliantly illustrates the real-world scale we're talking about. The chemistry is sound, right? But to make a real dent in global emissions, you need a massive amount of this specific rock. The Deccan Volcanic Province is an ancient volcanic landscape covering a staggering 500,000 square kilometers across western and central India. The researchers zeroed in on the main Deccan Plateau, specifically the Puna Nashik area and the Killary borehole. It's this vast expanse of basalt that exactly gives India that estimated 150 gigatons of storage potential. But to understand how we actually inject gas into solid rock, we need to look at how these rocks formed millions of years ago. Take a quick look at the researcher in this photo just for scale against this Pahoho lava flow. You can distinctively see a 3-tier structure. At the top, you have the upper vesicular zone, which is just full of holes from ancient gas bubbles. In the middle is the massive core zone, much denser rock. And at the bottom, the lower vesicular zone, again full of bubbles. This stacked architecture is exactly what dictates how fluid, or in our case, CO2, can move through the ground. Section 4. Sponges, pipes, and rock. Let's zoom in even further on our macro to micro journey. Imagine for a second that you're a single CO2 molecule trying to navigate your way through this ancient stone. How does a solid rock hold gas? Well, it comes down to porosity and permeability. Think of them as sponges and pipes. On the left, we have the vesicles, those fossilized gas bubbles trapped when the lava cooled. They provide the porosity. They act like a sponge, giving us the open space to actually hold the CO2. On the right, we have the fracture networks, deep cracks that formed as the lava contracted.
These provide permeability, acting like pipes that let the CO2 flow deeply into the rock matrix. For effective storage, you absolutely need both, a good sponge and good pipes.
Now, researchers also needed to ensure the depths of these rocks provided the right cooking conditions, so to speak, for our chemical reaction. By extracting samples from up to 327 meters deep, they calculated the environment down there, an ambient temperature of 34.8 degrees Celsius and a lithostatic pressure of 73.9 bar. At these specific depths, the elevated pressure and temperature create the absolute perfect reactive subsurface cauldron. These conditions dramatically accelerate the dissolution of the silicate minerals and the formation of that permanent carbonate stone.
Now, what's really interesting about this slide is that nature is rarely uniform. And this brings us to rock heterogeneous. The rock isn't just one perfect, uniform sponge. It varies wildly. Sometimes those little vesicle holes are completely empty and ready to hold CO2, but other times they're already clogged and filled with secondary minerals. The fracture pipes also change rapidly, from dense interconnected networks that allow great flow to isolated cracks that just lead nowhere. The crucial takeaway here is that you can't just drill a hole anywhere in the Deccan Traps and expect it to work. You need meticulous, highly precise mapping to find the exact right microstructures to ensure the CO2 flows correctly.
Section 5. A pathway to net zero. Pulling back from the microscopic fractures, how do researchers quantify this potential for the real world? Well, to calculate exactly how much carbon this massive volcanic sink can actually hold, they employ a complex methodology. Step 1. Get their hands dirty. They extract physical rock samples from deep boreholes and open field outcrops. Step 2. Takes those rocks into the lab. They use helium porostrometry, which uses inert helium gas to measure the exact empty volume inside the rock alongside high-tech micro-CT scans to visually map the pores. Finally, Step 3 uses discrete fracture network modeling. Basically, they take all this data and build a digital simulation to predict exactly how fluids will flow through that complex web of fractures. It's a rigorous process to ensure that 150 gigaton estimate isn't just a pipe dream, but a mathematically modeled reality. The scale of the global climate challenge often feels incredibly daunting, doesn't it? But the solutions we uncover can be equally awe-inspiring. By mapping the intricate plumbing of ancient lava flows, researchers are discovering that the very earth beneath our feet holds incredible untapped potential. It leaves us with a really powerful question to ponder. Can the massive volcanic eruptions of our deep past actually be the key to securing the climate of our future? Thank you so much for joining me for this explainer, and keep questioning the ground you walk on.